Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Deanna Hooper, Charlie to friends. I'm a postdoc currently doing, I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, a lot of cool stuff happening inside the universe. I love being a scientist, I love being a cosmologist, and I love getting to chat to everybody about all of the cool things I get to work on. So I see we have a lot of regulars coming in already. Let's see, who do we have here? We have Mito, we have Ben, we have James, we have Ange, we have Scott, we have David Howden, one of the Davids in already. Welcome back, everybody. Great to see you all here, and welcome if you're a first-time viewer. If you're not familiar with Cup of Cosmology, the idea here is that this is an interactive stream. You people can ask me anything you want about physics, about academia, about life, about cosmology, basically, and ask me anything. You can ask me whatever you want. And while I cannot answer every possible question, I will try my best to give you at least some answers. Hey, Paul, great to see you as well. And I still owe you an email. I am very aware that I have a backlog of emails. The last few weeks have been a bit intense. I've been doing way too many things, both at work and in my private life, to the point that I literally don't have time to reply to emails outside of work emails right now. So I know I still owe a couple of you emails. Those are on my mind. I'm very aware of that. But yeah, it's Also, my plants needed repotting recently. There's still some that need repotting, and obviously plants take over everything else. Hey, Prath, great to see you as well. Great to see all of the people joining. So you might notice if I change any detail about my introduction, I mess it up, because for years I've just been on doing the same thing of welcome to Cup of Cosmology. I try adding random things in, like I've added in the second name that I'm using now, and then it just throws me off balance, and I'm like, wait, yeah. So anyway, welcome if you're a first-time viewer. I hope you're prepared for some chaos, because these streams are often very chaotic. Welcome back if you're a regular. You know to expect chaos. If you're coming again, I assume you like the chaos. If you haven't done so yet, please do like the video, leave a comment, subscribe to the channel. It is super helpful when you do all of that. It really does boost engagement. I'm not sure what's happened the last couple of weeks. I think YouTube is doing A/B tests, and my videos have been pushed to a bunch of people, which is really cool. And I'm getting a lot more viewers. So thank you everybody who press buttons and make stuff happen on YouTube. I really do appreciate it. It really is helpful to me. Also, because now I'm getting a few more viewers, there's also been a few less than pleasant comments left on some of my videos, but I just delete those very quickly. If you happen to see a comment that is nasty, don't worry, I will delete it as soon as I get around to it. So thank you for those of you who leave me very nice comments. I do appreciate it. If you leave a nice comment, I always try to thumbs up it or like it some way, because I really do appreciate all of those who leave lovely comments on YouTube and who press all the buttons and make stuff answer. That is always very much appreciated. Paul, yes, I will reply to your email, and John, I believe I owe you 2 emails maybe. So I will reply to you all at some point, probably not today, but those emails are coming. Comment from Scotia, you got an answer on the question about the sun and moon being the same apparent size in the sky. It is a complete coincidence. The fact that we can have solar eclipses where the moon kind of eclipses the sun, this is a total coincidence. We just happen to live on a planet where the moon is the right size in the night sky and the sun is the right size, and they're all the right distance from us, because the sun is orders of magnitude bigger than the moon. But it just so happens that the moon and the sun are at the right distance from the Earth that we can get these very, very cool solar eclipses. Yes, we are indeed 90 degrees rotated from our normal view. I think last time I did the stream, that was also the case. I moved all of my furniture around recently, which now means that I am facing the window. My window is over there, which is much nicer, because then when I'm working, I can actually just look out at the trees and the sky and get very distracted. You used to see that wall, now you're seeing this wall. If you're wondering why there's an empty hook there, there's a picture that needs to go up there. I just haven't got around to putting it up yet, because again, chaotic life. Might be that one of my plants is going to move to the back here, so that then you see plants in the background to make it a bit prettier. But yes, this is going to be the layout, at least for the foreseeable future, because I kind of like this layout a bit better than the usual ones. So while this is usually let's talk about whatever random things people want to ask me, I do have a topic today. There was a very cool announcement this week. Unfortunately, contrary to what David just asked here in the comments, it is not related to space dragons, although invisible space dragons are still one of my favorite hypothetical universe scenarios. Not a very plausible one, but a fun one nonetheless. I see a comment from Ben here asking if there is any new info about the DESI project. So DESI, Whew, I am talking quickly, and it is way too warm to be talking quickly. It is like 25 degrees here today, which is ridiculous for Helsinki, and it's going up to 28 in 2 days, and I am not looking forward to that. On the plus side, on Wednesday and Thursday, I am lecturing at a cosmology school for undergrads, which is super cool. It's basically trying to recruit people to the dark side. So we have a bunch of very keen, enthusiastic undergrads. I think there's like 25 students, and we go to a nature reserve and just teach them cosmology for a week. And hopefully by the end of it, they'll want to become feature cosmologists. And I'm giving one of the lectures. I'm super excited about that. I know this is tangent, DESI on my mind. I was in the middle of answering. We'll get to that. Yeah, so I'm lecturing at this summer school for students, and I'm super excited. My task is basically to convince students that you can do cosmology on your computer. If you don't like maths, you can get the computer to do maths for you. That's what I do. And the nice thing is it's in a nature reserve on the outskirts of Helsinki, and there is a lake. And we've been told that the lake is a bit cold, but we're welcome to swim in it. So I'm super excited because on the hottest day next week, I'm just gonna, as soon as I finish my lecture, I'm gonna be in the lake. I'm gonna tell the students, like, if you have follow-up questions, I'm in the lake. That is where you will find me. So yes, 2 days next week, Wednesday and Thursday, I'm off on this cosmology retreat, trying to convince students to sign up for cosmology. And yeah, it's going to be fun. How many get distracted by the nature reserve and become naturalists instead? Probably a fair amount. But we are going to just a general nature park that has sports centers nearby. There are other like field labs that the university has where there's like insects and flora and fauna explorations, and those are super cool. We went to one of those last year. That was really fun. But yes, it's like you can learn about cosmology, or while you're here, go poke at the bugs and figure out what's happening outside as well. The students are welcome to do that. I believe most of them will come to the lectures, but there's plenty of time for everybody to go in the lake, to go into the saunas, because of course it's Finland, you can't do anything without saunas. There will be food. It's going to be very fun, but I'm especially excited about giving a lecture and throwing myself in the lake. About the lecture, I have not prepared it yet, and my lecture is in 3 days. It's going to be a busy week. Speaking of being busy, yes. So I see people saying 25 isn't that warm. I agree, except it is for Finland, because usually in the hottest months we get between 25 and 30. So it is hot for us, given that it is only May. And a lot of Finnish homes are built around the principle of keeping the heat in, because you need that in winter. In winter, when it's minus 20 degrees outside, you need the heat to stay in. We have triple glazed windows. We have things keeping everything inside, which is great in winter, but less great in summer. And all of my windows in my house are south facing. So there is a hint too much heat. But my apartment is still pretty bearable, all things considered. Yes, DESI, I was in the middle of answering that. We'll get to that. But there's just a comment here from Ant that then I'm giving a lecture in Cambridge. That is indeed true. So I'll be in this nature reserve Wednesday and Thursday this week. And then on Sunday, I fly to the UK to give a seminar in Cambridge, which I'm super excited about. Then I take a few days to wander around the UK. And then the week after that, I'm attending 2 conferences in parallel, and then hosting a birthday party where I've invited way too many people given the size of my apartment. So yes, conclusion is I'm busy. And the next 3 weekends, there probably won't be a cup of cosmology, because next Sunday I'm traveling. The one after I'll probably be exhausted from getting back home. And then the one after that, I'm hosting a massive party at my place. So the next cup of cosmology for sure will be the 23rd of June. I might try to do one between now and then, but I'm not yet sure. But you can assume there's going to be 3 weeks with no cup of cosmology because of all the things I just mentioned up above. I'm sure the content of the lecture will be important, but your passion for the subject is probably what will get the students. Thank you for that comment, David. I do hope that I can convince the students that it's fun. Also, I think all of us lecturing at this school are super passionate about cosmology. So I think it's also part of the point of this is just like, look, here's all of the different things you can work on, and look at how much fun we're having. So yeah, I think the content, as you say, is not the biggest thing. It's how we explain things. Also, I have cool interactive demos, and because I'm talking about computational cosmology, I can just be like, look, here's a simulation that I made earlier. Here's one I prepared earlier. Of course, with live demos, it's going to go wrong. But at least like a third of my lecture is going to be, here's a live demo. Now I can shut up and let the live demo do the talking for me, and then convince people, if you want to do these live demos, join Cosmology and we can do live demos together. There was something wrong with my charger, fixed it now. It is not my first time in Cambridge. I have been in Cambridge already once before, so I was there in 2018 also giving lectures. That was very surreal that my first time in Cambridge was as an invited lecturer. During my PhD, I felt highly unqualified. But yeah, I went there for 3 days. I was one of the 2 main lecturers in an event they organized. And it was really nice. I got to see a lot of Cambridge. But that was 6 years ago, 5.5 years ago now. So yeah, it will be really nice to go back. It's not my first time in Cambridge, and it's not my first time speaking at Cambridge, but it's really cool to go back there. I have good memories of that trip. And I remember seeing a lot of the really pretty buildings, and I think it's going to be really nice to go back there. Also, I know a lot of people there, so it's going to be really nice to go back there. Cambridge is a nice town. Worth some time if you've not been there before. Yeah, it is. I only have 48 hours in Cambridge, but I will get to see some things. So it's always nice. Yes, Press, that will be my birthday party. So my birthday is actually like at the end of June, but my birthday is just after Midsummer, which is the biggest party of the year here. Everyone in Finland celebrates Midsummer and then heads off to their summer cottages for a few days. So if I actually did my a birthday party on my birthday, nobody would be around. So I'm doing it like a week or so early. Yeah, I'm hosting a birthday party. If I've counted correctly, there are 28 people invited, plus a bunch of children, and my apartment is not that big, but I get to cook for 28 people. And if anyone knows me, that is something I love doing, cooking and baking and hosting a party. It's going to be so much fun. I will absolutely not be streaming that party. Absolutely not going to stream it, but I'm super excited about that. I should send out the official invitations, but yes. Next week I'll be traveling I'm going to the summer school, then I'm traveling to Cambridge, giving a talk, visiting people. Then I'll be traveling back, so no cup of cosmology. Then I'll be attending 2 conferences and then party, so no cup of cosmology for a while. Just thinking about this makes me exhausted. But it's going to be fun. It's going to be super fun. And potentially there's another conference the week after that I might have to skip because I kind of need to sleep. But it's going to be super fun. Big things coming up. Excited. Lots of stuff going on, but lots of fun stuff. Plus my social life is all over the place. And I'm doing way too many things. My plan was yesterday to have a relaxing day, and then I learned that there were 3 events happening in Helsinki, and I went to all 3 because why not? Today I baked a cake, so fun times, fun times. This is why I haven't gotten to your emails, those of you who I owe an email to. Okay, at some point a while ago I started answering a question. There was the question, I can't remember who asked now, of are there any updates about DESI? DESI is the Dark Energy Spectroscopic Instrument. It is a very, very cool telescope that is in Chile, in the desert, not in Chile, in Arizona, in the desert. The Dark Energy Spectroscopic Instrument is trying to measure, as the name implies, dark energy. It is taking a map of up to 6 million galaxies is the plan. It's already, it's going to get up to 40 million galaxies. It's already taken photos of the first 7 million. It had its first data release very, very recently. And I did a whole stream about the Dark Energy Spectroscopic Instrument and its first data release. In Arizona, started collecting data in 2021. I found my notes, in case you're wondering what I'm doing. I found my notes. It has the first data. I did a stream entirely about Dark Energy Spectroscopic Instrument, I believe in April, the first weekend of April. They found some potentially interesting results where the Dark Energy Spectroscopic Instrument seems to slightly disagree with our standard model of cosmology. Not going to go into too many details because there is a stream entirely about that already. But since April, there have been no new updates. So we're not going to get another update probably for a couple of months. Very, very cool results, very interesting. Everything about the results I already discussed on the first stream I did in April. I'll post a link to it at some point if I remember. I know I can make links appear on the screen. I've never figured that out, but I'll post a link somewhere in YouTube so you can find a link to that stream. And yeah, no new updates with the Dark Energy Spectroscopic Instrument just yet, but it's going to take a while. We just got year 1 data. It's going to take a couple months before. I imagine we're not going to hear anything more from DESI until 2025 at this point. The problem with having an army of plants is I also have an army of fruit flies. Are we talking about DESI? I was just saying, hi Abyss, great to see you by the way. I was just saying there are no new updates about DESI. DESI put out its first data in April. I did a whole stream about that. It's very, very cool results, but DESI is not the topic I want to talk about today. Today I want to talk about my favorite current telescope. So this would be Euclid. Euclid is the Dark Explorer, as I like calling it. Euclid is a telescope, a satellite that belongs to or funded and built by the European Space Agency. It is a satellite that was already launched in July last year, and its main mission is to create a super detailed map of galaxies going back billions of years, with the idea of trying to understand dark matter. So the universe, as we know of it, is made of three main components. Everything you see, everything you're accustomed to, everything from me to the stars we see at night to my coffee mug, all of this is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There's another 26% in the form of dark matter. Dark matter is this weird type of matter that holds everything together. It interacts via the gravitational force, but it does not interact electromagnetically. This means that dark matter is invisible, but it is the scaffolding of all other galaxies and everything else in the universe. And then there's a remaining 69%, which is dark energy. Dark energy is driving the accelerated expansion of the universe, and that's pretty much everything we know about dark energy. So I'm a cosmologist, so I study the universe. We only know 5% of the universe. The rest is this big mysterious thing that we're trying to understand. Euclid is one of the ones that is trying to help us understand this. So Euclid is a satellite of the European Space Agency. Its main mission is to understand the nature of dark energy and dark matter. It is going to map galaxies going back billions of years, so then it sees how galaxies have progressed through different epochs of cosmic evolution. This allows us to see how they cluster together and how they're now being pushed apart by dark energy. So the main science objectives of Euclid are to measure or to help us understand dark matter and dark energy. This is an artist's impression of what Euclid looks like. Now, Euclid had been in development for as long as I could remember. When I started my PhD, Euclid was hyped up. It's always been the mission I've been the most excited for, apart from the gravitational wave ones. Last year, on the 1st of July, Euclid launched. It was a perfectly successful launch. There were no issues. Euclid has been sent to Lagrange point 2, which is a stable point where it's kind of on the other side of, if you consider here you have the sun, here you have the Earth. Lagrange point 2 is kind of over that way, so it's shielded from the sun by the Earth. And it's in a stable orbit, so it doesn't need much, and it's just going to stay there. This was July last year. Now, Euclid is planned to be a 6-year mission. It's going to take 6 years of data. But before it can start taking all of the big, massive data, there are several tests that need to be done. The first one, well, there were a bunch of them, but one of the first ones that was done already in November last year was to check that all of the cameras were working properly. So in November last year, we got the first 5 images of Euclid. These were released in November. You might have seen them. I did a stream about them as well. We had different galaxies. We had the Perseus cluster. We had the nebula, here the Horsehead Nebula. These were the first 5 images that were released by Euclid team, and these were just kind of a proof of concept of like, look, we know what we're doing. We can take cool photos. Now let's get down to science. JWST and Euclid are indeed neighbors in L2. There's a few satellites in L2 just because it's a convenient place to park our satellites, so we just throw them there. They're far enough away from each other that there's no chance of them crashing, knock on wood. But yes, they are just kind of parked in L2. Need to remember to drink more in the heat because otherwise I'll be dehydrated. So yeah, Euclid is equipped with 2 cameras. One of them is VIS, which does visible light, and then it has the NISP camera, near infrared spectroscopic and photometric camera. So it does spectroscopy and photometry. Basically, it measures the distance to objects and it measures how much light you're getting from objects, and it can take pictures in infrared. So Euclid can cover visual and infrared. Now, these images that were released last November, this is again kind of like the proof of principle. This is not one of the main science goals of Euclid. This is just like, look, our cameras are working, we're doing things, This is what we're doing here. We're working. But these pretty pictures that you get from JWST and from the Hubble Space Telescope, this is not the type of pictures we should get often from Euclid. We had these first ones in November 2023. Since Euclid, comment here from John, since Euclid and DESI will both be creating detailed surveys at the same time, are there ways the two datasets can be combined? Absolutely, yes. Now, the big difference is if you're ground-based, you generally can only focus on a bit of the sky because you're limited to as the Earth is moving around, but you can stare at that part of the sky very, very intently. So DESI can stare very intently very intensely at one patch of the sky, whereas Euclid can look all the way around. Usually you want to combine a ground-based and a space-based mission in order to really get more data. However, here they are looking at quite different things. So they are both kind of mapping galaxies. Euclid is mapping them to then kind of using cosmic shearing, so how galaxies are, different ways in which galaxies are distorted and building the distance towards them. Euclid is more focused also on using distortion of galaxies, but it's going a bit further back in time. So we can combine them for different aspects. We will combine them. And of course, the DESI results, now we need Euclid information as well to kind of agree or disagree. So Euclid and DESI data will absolutely be combined, but they have slightly different objectives and slightly different ways of looking at the universe. So they are in no way superfluous or competing. They're doing different things that is highly complementary. And we will be able to combine them a bit. So Euclid and DESI, ideally, at some point we'll have all of the data from both, and then we can create them incredibly detailed map. DESI is focused on dark energy. Euclid is focused on both dark matter and dark energy. We'll put them all together. So Euclid, first data release or first images released in 2023, November 2023. And we were all told that the first cosmology data and the first actual data release would be in early 2025. That is still the case. Early 2025 is when we're expecting the first kind of preliminary cosmology results, maybe the first preliminary cosmology data. And then last week, Euclid called a press conference. And they advertised that they were going to release their first set of images, of actual science images, with the first publications. So there was a press conference on Thursday with the first 5 actual science images and publications. Now, this is amazing. This is very, very cool. And before I jump into what each image is and why these images matter, I want to talk a bit about the fact that these images exist and this kind of early science that is being done. So often when you launch a spaceship, or spacecraft, people expect some type of pretty images. You know, we had these, again, these are the November ones from last year. These are pretty images that you can splash on your newspaper cover. They're very catchy. They get a lot of attention. But it is not one of the main science goals of Euclid. It's like, look, we can take pretty pictures because it's kind of what's expected of spacecrafts. They're going to take pretty pictures for us. However, you can also do pretty pictures and science at the same time. So as a second stage, the first stage was these images that are just like, look, our cameras work, we're taking pictures. As a second stage, they have what is known as the early release observations. So the early release observations are targets in the night sky that serve 2 purposes. One of them, catchy pictures that you can prove that your cameras are working well and that you can give to the public as like, look, this is why we built this thing. But also at the same time with a science objective. So Euclid put out a call a couple of years ago of like, pictures are an idea. If you had a few hours of observation, you can point this satellite wherever you want for a few hours. What can you do with it? So a bunch of people submitted proposals of like, okay, give me 5 hours of observations and I'll do this. And part of the proposal was justifying the public interest in this object, and part of it is justifying the science you can get. Out of these many, many applicants, I believe 7 or 8 were selected, and these are what are known as the early release observation program. And these are the images that were released last Thursday. So they're images that serve 2 purposes, a science one and look, we've got a pretty picture one. And I think it's really, really cool because sometimes you might have an objective that doesn't really justify building a whole spacecraft, but you can kind of benefit from somebody else doing these observations. So I think this early release program is really, really cool because it's kind of like, what can we do? You know, you have a few hours. I did not make a suggestion because what I'm interested in is the main target of Euclid, you know, what Euclid is doing. And these other suggestions are tangential to the main target. It's like, it's not really dark energy, dark matter. It's just, what else can we do? What else can you do? They're very, very cool proposals, and they're usually slightly more on the astrophysics side of things rather than the cosmology side of things. Because when we get these images, like again, I'm going to show the November ones, when you get this one of like the Horsehead Nebula in the top center, you can study a lot about gas clouds and about star-forming regions. So these are images that you can really use to do some kind of close-by science, in quotation marks, because you'll see these objects are not close by. But I think it's really a nice way of showing how when we build a telescope, it's not just the main objective. There's always the side quests. And these are kind of 5 side quests that Euclid was able to do while gearing up and preparing for the main mission. So at the press conference last Thursday, which I actually missed because I was giving a seminar at the time, but there was a press conference last Thursday where Euclid released 5 images, each one with an accompanying science paper, plus 5 more papers about the whole spacecraft, the cameras, the testing, the kind of, are we sure that what we're doing is correct, how much noise we're going to get. So 5 kind of more on the this is what we built side, and 5 of these early release objectives. And these early release objectives are super cool, and I'm going to go through all 5 of them. I see there's a question here about the 3-body problem. So I do kind of want to stay on Euclid stuff today, so I'm just going to answer very, very quickly. The question here is, why is the 3-body problem unsolvable? I suppose if all the metrics of all the 3 bodies are known, then it should be possible to know their position at any given time. It's not that it's completely unsolvable, it's that it is impossible to calculate, basically, because so if you want, yeah, this is going to be a very long answer, so let's try to do it briefly. The 3-body problem is when you want to have, for example, one central system like a sun and 2 planets orbiting around the sun. This is not very stable. There are very few positions, or if you have 2 suns and 1 planet orbiting around them. This is something that is highly unstable because you have 2 massive objects or 3 massive objects, and it's very difficult to figure out how each one is going to move. And you need to calculate this many steps down the line. So the 3-body problem is kind of like, how do you get a planet in stable orbit around 2 suns? And most combinations that you can come up with will end up with a planet crashing into one of the 2 suns, into one of the 2 stars. So that makes it very, very difficult to find a stable solution. And it is also very difficult to calculate what is going to happen because you have to follow all of the forces happening on all 3 objects over the entire time that you're studying. So it becomes very difficult to calculate. 2-body problem we can solve, 3-body problem is like, nah. And then you move up to n-body problem and you throw that at a computer. But yeah, the 3-body problem is kind of the idea of how do you keep a planet in stable orbit around 2 stars, and this highly depends on the initial configuration, on the masses of the planets, on the on the distance. So there's a lot of computation that goes into it. So it's very, very hard to map everything. And you can have random movement. So it's just very, very difficult to map. Okay, back to Euclid. Star Wars is a lie. Unfortunately, I cannot vouch for the scientific accuracy of Star Wars. For most things. Yeah, it would be cool if we could have things like lightsabers or force fields, but yeah. And yeah. There's some things about Star Wars that are very cool, but most things in Star Wars are not scientifically accurate. But that's why it's called science fiction and not science fact, right? We don't watch it for scientific accuracy, we watch it for fun. Okay, so back to Euclid. 5 new images released, each one with physics and pretty pictures. So let's jump straight into the very first image that was released last week, which is this one here. So this here is Abell, they call it Abell. Abell 2390. Abell 2390. This is a galaxy cluster. So every image here, every dot you can see here is a galaxy. This image contains over 50 million galaxies. There's a ridiculous amount of galaxies in this image. So this is the first of the 5 that Euclid released last week. This is an object that is, or this cluster of galaxies is 2.7 billion light years away. This means that we're seeing these galaxies how they looked 2.7 billion years ago. So this really is giving us a window into what the universe looked like 2 billion years ago, almost 3 billion years ago. This image with 50 million galaxies took 3 hours of data. So 3 hours of observations to produce this image. This is incredible. Euclid is going to run for 6 years. This image here was produced with 3 hours of data. This was one of the early release objectives where it was like, Euclid, point here for 3 hours and map these galaxies. So we have this cluster of galaxies. Now, this one is cool for several reasons. On the one hand, you can already see some distorted galaxies here, especially on the Euclid webpage. There's zoomed in versions of this. And you can see a lot of galaxies are distorted because of gravitational lensing. And gravitational lensing is this idea that light coming from a distant star or a distant galaxy can be distorted by big gravitational objects. So if you have a galaxy or a clump of dark matter, for an example, that's going to bend space-time, and the light traveling towards you is going to feel the curvature of space-time and distort. So then when you look at the galaxy, you're going to see a distorted version of the galaxy because it's a lens by gravitational effects. In this image here of 50 million galaxies, you can already see a lot of these galaxies are lensed, they're misshapen, they don't look the way they should. This is a big proof that Euclid can measure galaxy lensing. This is one of its key objectives. So, part 1, we have a pretty picture. Part 2, this is proving that Euclid can measure galaxy lensing. But of course, there was the individual science objective of this paper. And this one had the objective of helping to establish the masses and the number of galaxy clusters. So how many galaxies we have in this type of cluster and the different masses of these galaxies. So if you look at a galaxy cluster, in this case, Abell 2390, you can really get an idea of how many galaxies there are and the interplay between galaxies. So this lets us measure how galaxies progress over the course of the universe. So this is essential for cosmic evolution. So this first image, pretty picture, proof of galactic lensing, and we can use it to measure the masses and number of galaxies in galaxy clusters, which is information we can use to figure out how galaxies evolve and how that impacts cosmic evolution. If the lensing is due to stuff in between, would all galaxies that are in the same distance all be lensed the same way? Yes, they would. That is a very good question. Let me, in fact, go 5 slides ahead. 5, is that correct? Is this the slide I want? Let me see. No, 4 slides ahead, maybe. Let's this one here. So this is an example of what gravitational lensing looks like. So we are the Earth down here, bottom left. We're looking at the light of a distant galaxy, which you see here, top right. In between the galaxy and us, there's this big clump of thing that we call dark matter because we can't really see what it is. You can see this galaxy is shooting off these white light beams. As these white light beams come towards you, they get distorted by the gravitational lens. When they reach us, we trace them back as these orange arrows here. This means that we see multiple images of the same galaxy. Any galaxy that is equally distant would be lensed in the same way, in the same direction. Now, it very much depends. The further away they are, the longer the light has to travel, so the more or less it's going to feel the distortion. But the overall type of distortion is going to be similar if the lens is the same. So if they're distorted by the same image, by the same object, they're going to look very, very similar. So yeah, we can use gravitational lensing to measure the distance to galaxies and, more importantly, how much mass is between us and that object, because based on how much it's lensed, you can figure out how much gravitational force there was and therefore how much mass you have. So I am getting out of breath very easily today. I forgot that I had tea. The problem with doing a lot of things when I have long COVID is that my body crashes and then I get out of breath very easily. Dark energy does not have an effect on the gravitational lensing because dark energy is really just pulling, it would on really large scales, But here we're really talking about individual scales, so like small galaxies. We're talking about individual galaxies, so small scales. So dark energy doesn't really play such a big role here. It's really dark matter that is causing these objects to be lensed. So there's a comment from Abyss here that you're looking at the full image and it is breathtaking. And I agree. You know, the images that I'm showing you here are not going to do justice to the real thing, because you're looking at them on a screen, you're looking at them in a very small place. You know, absolutely, please go to the European Space Agency Euclid webpage and look at the full resolution version of these, because what I'm showing you here does not do it justice. This is a 2.8 megabyte version. The one you can get on the ESA webpage is 28 megabytes. So, you know, this does not do it justice. So we cannot yet measure BAO signal in Euclid data because we don't yet have enough to do that. We need a huge collection of galaxies. That is something for later down the line. That is not a now thing. You have photographed Abell 1656. It's really nice. Yeah, if you have a camera and a telescope, it's very fun to try to take pictures of different clusters, because you really get a lot of cool information there. It's just fun to take photographs of these different things. Yeah, I define a galaxy as small scale, but then to be honest, this image is a tiny, tiny patch of sky, and there's 50 million galaxies here. So yeah, it is. Galaxies are, I'm afraid, these tiny little points here. They are small scale on cosmological scales. What's one galaxy when there's billions of galaxies out there? Okay, on to the second image, and one of my favorites. I love all of these 5 images. On to the second image. The second image is Messier 78. This is a nebula. I love nebulas. Nebulas are places where you can form young stars and planets. It's basically a star nursery. This is Messier 78. It is 1,300 light years away in the Orion constellation. It is not the Orion Nebula, but it is part of the Orion Nebula. This amazing image here was taken using both cameras on Euclid, so the visual one and the infrared one. This image used 1 hour of observation data. 1 hour. Euclid is going to run for 6 years. This is 1 hour worth of photos. This is amazing. This is so cool. Okay, so apart from being an incredibly pretty picture here, it's just so pretty. Apart from being very, very pretty, this one has the purpose of trying to understand how stars and planets are formed. Now, what is new here with Euclid is you can really start to see the filaments. If you look right at the center of this nebula, you can see these gassy filaments, and these gassy filaments are essential to planet formation and to star formation. So by looking at this image here, the science paper that came with this talks about the gas filaments, the dynamics of star populations, how stars are formed, how stars are born. This is very, very cool if you think about it. This is not even one of the main objectives. This is kind of a byproduct of Euclid. Euclid was just like, hey, do you want me to point over there for a few hours? Sure, I can do that. And now we have a paper talking about how planets and stars are formed with 1 hour of data. And this is why I love these early release targets, because it's really like, what can we do as a side quest? Main quest is dark matter and dark energy, but hey, also look, I can look at how planets are forming. And that is so cool. That is really, really, really cool. So yeah, this is one of the prettiest images. Again, on the webpage, there's a high-res version and there's zoomed-in versions of like, look, here's a filament. This is important. Here's another filament. Here's a baby planet. Here's a baby star. It's really cool that we have this one. Format for the M78 is over 250 MBs. Yes, this version is 3 megabytes to fit it in my slides. The full version on Euclid is massive, massive, massive. It is absolutely amazing. Okay, some questions here. What's the demarcation between a galaxy and a dwarf galaxy? Kind of the size. I can't remember off the top of my head, but a dwarf galaxy is less than half the size of the average galaxy, and dwarf galaxies are often found orbiting around normal galaxies. Does gravitational lensing also cause diffraction, or do all wavelengths of light get refracted equally? All wavelengths should get refracted equally, because we're really just talking, so if the light going into the lens consists of all possible frequencies, the light coming out will also consist of all possible frequencies. It's not like when you have a normal lens where, like an optical lens, where you can have kind of the rainbow effect, like with a prism. There you really are splitting the wavelengths. In the case of the gravitational lens, what you're moving is the path the photon is taking, so it doesn't actually affect which wavelengths come in or out. It just affects the path that the light is taking. So all wavelengths get refracted equally with the gravitational lens. Dorado, if you want to share a link to a 20-hour exposure of the Orion Nebula, please do so. Please feel free to post a link. If it doesn't let you, you can put it there, and I think I can authorize it after the stream on YouTube. So feel free to post it. Science images are always welcome, and especially, if you've taken very cool space pictures, please share them with the world. Tell us about it. You're absolutely welcome to post your link to the Instagram video or whatever you want to post with your space image. Please go ahead and post it. Maybe just include in the picture, in the comment, this is the space photos, and so it's not just a random link. If YouTube doesn't let you post it, we can post it later. Please go ahead for that. Okay, so we've seen the first one. Now we've seen Messier 78, which is many people's favorite. It is very, very, very pretty. You just shared it. I cannot see it, so I might have to authorize it later, because at least it didn't come through to restream. So I'm not sure. I will check later and see if I have to click a button to let it show. But if I do, I will do that at the end of the stream. I don't want to open YouTube and try to do that now. That will confuse me. Okay, 2 down, 3 to go. Let's go on to the next image. Next image is NGC 6744. Slips off your tongue. I have taken notes because I am not going to remember these names. Yes, I know it is on the slide. I put it on the slide. I'm not going to remember these names. So I have notes today. This is a galaxy, a spiral galaxy, as you can see, that is about 30 million light years away. So this is how this galaxy looked 30 million years ago. Again, this is 1 hour of data. This is staring at a galaxy for 1 hour, and this is what Euclid could produce. Absolutely amazing. This galaxy is often called the Milky Way's twin. It has the same overall structure. It has the same overall shape. I don't see so much blue color correction, though. What's wavelength range for Euclid? I'm not sure off the top of my head. It is visible and infrared, but I'm not sure exactly the wavelength range. I think that information is on the Euclid webpage, but I don't have it written down. So this is considered the Milky Way's twin because it has the same amount of arms. It's a spiral galaxy. It's the same overall shape, same overall size. We can't really get these photos of our galaxy because we are in the galaxy, and it's very hard to observe the galaxy when you're part of it. But by observing this other one, we can basically get a proxy of this is what our galaxy could easily look like. This could easily be our own galaxy. So here we get a pretty picture. That is Earth's twin, or not Earth's twin, sorry, the Milky Way's twin. And here is really where we start to exploit the fact that Euclid has 2 cameras, and it can look at the large scales and the small scales, because you can see the overall galactic structure. But if you zoom in, which again, this is the low resolution version, if you zoom in, you can actually see the structure in between the arms. You can really see the dust in the galaxy. So there's also filaments. You can just about see them at the edges of the arms. It's kind of like filaments that are breaking off. This is letting us study how galaxies form and the interplay between galactic dust and the arms of the galaxy. Also, because this is 30 million light years away, we're seeing what a galaxy looked like 30 million years ago. So we can also get a bit of an idea of how this galaxy is evolving over the course of time. And as a bonus, with this image, people discovered a new dwarf galaxy that they didn't know was there. One of the small blobs is a galaxy orbiting around NGC 6744 that people didn't even know was there. So this image, pretty picture, has met that goal. It's a proof of principle again that Euclid can probe individual galaxies. It's letting us study how gas behaves inside galaxies. It looks very much like our own galaxy, so that's a nice bonus. Also, as a nice bonus, they discovered a new galaxy with this image. And we have filaments around the outside of the galaxy, which is really cool because people weren't completely sure if these would or wouldn't be there. And now we can map them. So this is 1 hour of Euclid data. Again, Euclid will take data for 6 years. And just look at what it was able to do with 1 hour. And I really want to emphasize the importance of these side quests. I'm calling them side quests, but I don't mean to detract from how important they are because it's proving what Euclid can do while doing cool science on the side. It's like bonus science. I love science, and bonus science is like, hey, you get this for free. I mean, not for free. Euclid wasn't free. But this is not the main target of Euclid. It's just like, while I'm here, I'll just take a photo of a galaxy for you. Presumptuous question. Ooh, sounds exciting. With all these new telescope findings, when do we find out our understanding of the universe was wrong? That would be very fun. I think that's something that a lot of us would be very excited about. You know, if the dark energy spectroscopic instrument results are correct, our standard model of cosmology is wrong. And that is super exciting because that means we have to go back to the drawing board. It's where we start playing again. It's where we start figuring things out again. So it's not really a foregone conclusion. The foundations are pretty strong just because so far we haven't found anything that refute them. But the more data we have, the more we can poke at our theories. And this is what we do as scientists. We come up with a theory and we poke at it until it falls apart. We throw every data set we have at it until it falls apart because then we can build the next theory. And science is continuously progressing, evolving our theories, expanding our theories as we get new data. So getting all of this new data from new telescopes is either going to show, like, yes, the foundations are so solid you cannot possibly knock it to the ground, or it's going to knock it down or start poking holes in it. And then this hole, sometimes you can fill them like, yeah, there's just a small misunderstanding. And sometimes you have to throw out the theory and start again. And that is where the fun begins. So I think the data we're getting from these new satellites is super exciting. But it's not yet time to throw out all of cosmology just yet. But there are definitely things worth keeping an eye on, like the new DESI results. We still have 2 images to go. My laptop is overheating. I am overheating. My tea is still hot. Everything is hot. Let's move on to image number 4. And it would help if I put it back on screen. So let's bring that back on screen. Reminder, PSA, everyone watching, please give this a thumbs up. Yes, please do thumbs up, like the video, leave a comment, subscribe, all of the usual YouTube things. It really, really does help. I really do appreciate when you all do that. This is Abell 2764. This is a cluster of galaxies that is 1 billion light years away, which is quite close on cosmological timescales. It's 1 billion years. This is 3 hours of observations. Now, the actual cluster of interest here is the one you can see in the top right. You see in the top right, there's this kind of smattering of galaxies up there. There's like several hundred of them. That's actually the main target here. But the idea was to see, can we get the main target plus other things? The purpose of this is we're looking at galaxies 1 billion light years away. And some of the that's a cluster, but some of the background galaxies here are some of the oldest galaxies that we know of. So we have top right, the super newish cluster, and then we have this background of galaxies. Some of the galaxies, some of the dots you can see in this image are over 13 billion years old. So some of these galaxies were formed when the universe was only 700 million years old. So this is, again, a really big proof of how far back in time Euclid is going to allow us to look. We're looking at galaxies that are 13 billion years old. This was 3 hours of data, and we have galaxies in this image that were 13 billion years old. If we could map all of these galaxies 13 billion years ago, plus the ones in the foreground that are 1 billion years ago, that gives us 13 billion years of cosmic evolution. That is amazing. That is going to show us so much. So this is, again, pretty picture, proof of what Euclid can do. Plus, we can actually see something very cool here. In the bottom center of the image, you see there's this really bright star. This is a star that is in the Milky Way. It is a close-by star. You can you can tell that it's a close-by star because it has this hexagonal refraction. This kind of stereotypical star refraction is what you get because of the mirrors that we have in Euclid, because the telescope build itself. But you see the refraction is much less than in other telescopes, in other satellites. And this is really cool because one concern with these experiments always is, are close-by stars going to block view of what's happening behind? So one thing they wanted to show with this image is that even though we have this close-by star, we can still pick out the cluster in the top right, and we can still pick out galaxies that are 13 billion years old. So, yeah, this image really shows us how clusters behave, how distant galaxies look, and what we're expecting to do with Euclid in the future. And there is a science paper with this as well. I see there's a couple of questions, and then we'll go to the final image, which is my second favorite, or one of my joint favorite with the nebula. Measurement question from Paul. If I say something is 1 billion light years away, is that how far it was when the light was emitted, or how far we calculate it to be now? Excellent question. So when we say something is 1 billion light years away, that is how far it is now. That means it sent its light to us when it was much closer. So technically, if something is 1 billion light years away, we're actually seeing it how it looked when it was slightly less than 1 billion light years away, because that's how far away it is from us now. Because the universe is undergoing accelerated expansion, objects will kind of send us their light, but keep traveling away from us. So by the time we get the light, the object itself is much further away. So when we say, this light is 1 billion has traveled 1 billion light years, that light is showing us was produced 1 billion light years ago, or 1 billion years ago, sorry. But by now, that galaxy, that object that we're looking at, is even further away. So when we say the distance to these objects, it's not necessarily how long the light traveled towards us, it's their distance now. So there is a slight nuance here because of the accelerated expansion of the universe. However, when we're talking about close by objects like 50 million light years, you don't need to care so much about the expansion of the universe. Now, these size galaxies that are like 13 billion years old, those galaxies are more than 13 billion light years away from us. Those are very far away from us now. Comment from Abyss here. You'll share the paper. There's one There's one research paper that suggests that cosmological observations could be significantly different depending on where you are in the universe. Yeah, that is one idea. Unfortunately, or fortunately, we have a lot of evidence that shows the opposite, that shows that wherever you are in the universe looks the same. This kind of isotropy and homogeneity of the universe is something that is pretty well established. So even though there might be some papers saying that that's not the case, they're going out quite a lot of data and literature proving the opposite. So it's very interesting if that's the case, but I feel like that's going to be a pretty big claim that's going to be pretty hard to back up, given all of the evidence we have saying the exact opposite. But it is very cool. Please do send me that paper. I'm happy to poke at it and take a look. Question from John. If Euclid is mapping dark matter using cosmic shear, can that map be used to narrow down what dark matter is made of? Yeah, so Euclid is using cosmic shear and mainly galactic lensing. So it's using the lensing, how much galaxies are distorted because of the lens. And it's going to try to figure out how dark matter behaves, which might tell us what dark matter is made of. One possible scenario is that we confirm the standard model of cosmology, in which case we say dark matter is cold, doesn't interact with anything, we don't really know what dark matter is. However, it could also find that, for an example, dark matter has self-interactions, or it could find that dark matter interacts with other things. So it might not necessarily tell us what dark matter is made of, but it will help us understand more properties about dark matter. So it might not tell us dark matter is made of space dragons, but it will probably tell us this is how these space dragons that look like dark matter behave. So no, it won't directly tell us what dark matter is made of, but it will allow us to figure out more properties of dark matter, which is very cool. I wonder if Euclid will record the Corona Borealis supernova expected this year. I don't think that's one of its targets because that supernova is super close by and Euclid is looking a bit further out. So I don't think that's one of its planned targets. I don't think it's one of the early release objectives either. I'm not completely sure, but I would say no. But it would be very cool. Okay, final image. The last 3 streams I have gone over 1 hour, and the last 3 streams I have had more views than the previous ones. So I'm starting to see a trend here that if I go over 1 hour, YouTube boosts my video more than if I stay under 1 hour. So maybe going forward, I'm going to aim for 1 hour and 5 minutes just to see if that tricks the algorithm. If nearby stars don't mess the white calibration, I wonder if that's going to affect the Starshade program. I'm not sure, actually. Haven't thought about that. That is very cool. So the Starshade program is kind of a shield that can block out the light from stars to look at exoplanets. It hasn't launched yet, but it's a very cool idea. I'm not sure how that would affect things here. We haven't expected supernova this year. There is a supernova expected. I'm not sure if this year or next year, but there is a supernova expected at some point, but it's probably not going to be one that will be visible during the day or even visible without instruments. It's going to be one that's like quite far away. We're not expecting Betelgeuse to go supernova or something like that. So I don't think it's one that people within the scientific community are excited about because we can stare at it with really big telescopes. But I don't think it's one that we're expecting to be visible unless you have very good telescopes. So I don't think it's kind of a widespread look out for this cool astronomical event. Just there is a star that might go supernova at some point. But I will have to check the details of that. I don't have that in my mind. Just like it's going to happen, but I feel like there's always supernovas going off somewhere in the universe. We just happen to be far away from them, which is a good thing. Okay, final image, the fifth image. Let's bring up my slides again. This is the Dorado galaxy cluster, or the Dorado galaxy group. It's not a cluster, it's a group. This is 62 million light years away. And this is, again, 1 hour of observation data. 1 hour. It's just 1 hour. And look at this. Look at this. Now, the reason Dorado is so cool is because it's a bunch of galaxies that are merging together. So it's a bunch of galaxies of different sizes, of different ages that are merging together. And some of the galaxies are still really, really young. So some of these galaxies that are merging are still forming stars. So this means that we're actually going to get to see how star formation is impacted by galaxies smashing together. Because suddenly you're going to have a lot more dust, you're going to have a lot more stuff flying around. So does that impact how stars form? So with this image, you can really actually watch galaxies merge. We can see galaxies merging in action. And this is actually a zoomed in version. The high res one shows you many more galaxies in this group. But if you focus on the two galaxies, you can see here the big bright ones on the top right, like middle right. If you look in between them, you can start to pick out this kind of cloud of dust merging between them. Merging is a polite word for what is probably a huge mess of galaxies combining. Yeah, we say merging because smashing together at high speeds sounds a bit more crashing together dramatically. Is a bit like, oh, they are merging gradually. Yeah, it's more like this is not a gradual git merge. This is a git collide. So two repos together, very nerdy reference. Yeah. Now, looking in between these two galaxies, you can start to see the gas cloud forming in between them, the way they've already started to merge. And this is really, really cool because this really allows us to see how the merging process takes place and how these different tidal shells are forming. So the tidal shell really is a shell of gas that is forming around the colliding galaxies. Measuring how mergers behave will allow us to learn more about galaxy formation, maybe even supermassive black holes if the two black holes in these galaxies merge. So this is giving us a lot of information about how galaxies merge together, what they look like, and what happens to stars that are forming in galaxies that are merging together. Also, every galaxy that we know of is embedded in a massive halo of dark matter. Watching galaxies merge together, we can figure out how dark matter behaves in merging galaxies. So even though you might all think that, the nebula one, let me just go back to it because it's super pretty again. This one here, come on, slides are thinking. This one here is absolutely gorgeous. This is a spectacular image. And most people think this one is this is most people's favorite. But if you're wondering why it's not my favorite, it's because if I go to this one here, the Dorado one, this is really leaning more towards what Euclid is meant to do. This is measuring dark matter halos. This is measuring galaxies colliding. This is a proof of principle. This is like, look what we can measure with 1 hour. Can you imagine what we're going to get after 6 years of data? It's incredible. So these 5 images, sure, they're pretty pictures, but they're also the first real science pictures of Euclid. We have not just here's pretty pictures, like here's pretty pictures with proof of principle of what Euclid is doing, and here's a bunch of side quests that lead to more understanding about how galaxies form, about planets, about nebulas, about gas filaments. There's so much happening here. Could you use the background galaxies to see how dark matter is behaving in the merge? Yes, you can. That is an excellent point here, John. Because we have dark matter halos colliding, this is going to produce gravitational lensing. By looking at merging galaxies, we can figure out what the dark matter is doing in these merging galaxies. So that's kind of cool. It's really amazing when we think about how much is contained in these images. And this is why I'm actually going to change the title. This is not Cosmology News. This is Euclid First Results, because that was the main topic today. I'm going to change the title and the thumbnail of the stream. This is not just Cosmology News. This is Euclid. We've been waiting years for Euclid to launch, and now Euclid launched last year, gave us some pretty images, and now it's starting to give us actual science results. Also, the data in all of these images is publicly available. Not only did they give us the images and the science papers, they were like, here's the data, go poke at it if you want. It is publicly available. This is really cool for me, apart from the fact that I love pretty space images. You know, pretty space images are my jam. That's what we like. I like pretty space images. Apart from pretty space images, we are getting first science results from Euclid. We are actually starting to see what Euclid is capable of. All of these images were taken in one day. It needed less than 1 day to get all of these images. You know, this is 1 day of data to produce these spectacular images. And imagine what we're going to get with 6 years of data. Now, again, these we're not going to get pretty images for every day of data. This is just like pretty images and amazing science happening at the same time. With the 6 years of data, do not expect many more of these pretty images, but we are going to get a lot more data, a lot more science coming out. This is just the beginning. And we haven't even gotten to cosmology results. Like, you can see how excited I am today. And basically what I've told you is Euclid works. We have pretty pictures. Here's some astrophysics stuff. Imagine next year when we start getting cosmology results. I think I'm going to be so ridiculously excited. So let me just go to comments here about the supernova. Comment from Abyss. There is a supernova expected later this year. It's a binary system that appears to go supernova every 80 years, exactly. It is not like a once-in-a-lifetime event. It is not overly dramatic, but it is something cool that is going to be happening. There's going to be a lot of amazing images over the next 6 years. Yes, there's going to be, more importantly, a lot of amazing science. And I love that apart from pretty images and like Euclid is working, we have these side quests, these early release, and this was 5. There was more than 5 programs selected, so there's still more coming. And it's really cool. It's like we built this amazing telescope, flew it out to space. This telescope is going to measure galaxies billions of years in the past, and also it's letting us understand more about star formation and about planet formation and about merging galaxies. It's amazing. How much analysis goes into taking that image and determining the distances and masses of all of the galaxies in it? So much. So I'm not going to downplay it. This is an incredible amount of work by a lot of people. And if you go to the European Space Agency webpage and look at these images, they have more details on how the images are produced, what went into them, what cameras were used, and the breakdown. But if you think these images were probably taken late last year, it takes months to process and to get what we have. And this is early days. It's expected that once, what do you mean every 80 years? Aren't supernova one-time events? Depends on the type of supernova. Some stars can basically burp and then burp again. But that's a conversation for the next stream, maybe. So once Euclid is fully operational, it is fully operational. Once we start getting the cosmology data from Euclid, we are talking about petabytes of data being downloaded. The amount of data we're getting from Euclid, one of the biggest problems with these missions is how do we store and manage this much data? Do we have the software ready to deal with everything we're getting? And that is a big question. And the amount of work, sure, we have pretty images here, and these pretty images come with a huge amount of effort by a lot of people. And it's not just like we point a telescope and now we've got a pretty picture. There is a lot that went into these analysis, and a 1 hour stream will not do them justice. Like these images here, this one here, to get this level of color, this level of detail. Sure, the spacecraft is amazing. It took this amazing photo, but then a bunch of people had to make this happen. And that is very, very, very cool. So also, if you think about it, like these images are 1 year of data and they took so long to make, but that's true with every space image. If you think of, for an example, the cosmic microwave background radiation, this is an image. I took myself off camera here. That was not intentional. Here we go. Took myself off here. This image is one that took 6 years of processing to produce it from the raw data. This is a snapshot of what the universe looked like 380,000 years after the Big Bang. This was a compulsory viewing because we went a whole 1 hour without a CMB appearance. Unacceptable. So this was just to make the comparison. All of these space images require a huge amount of processing. The ones that we have from Euclid, the new images from Euclid, involved a lot of effort. And I do strongly encourage you to go to or go to the webpage and check out the high-res version of these images, because what I just shared is the low-res version, and it does not do them justice. And it's so fun to look at the high-res ones and just zoom in and see how much you can zoom in. You can download the 30 megabyte version, 250 megabyte version of one, and just zoom in and zoom in and zoom in. And it is very cool. So yeah, Euclid has been my favorite spacecraft for a long time. Of course, I have a soft spot for LISA because that's the one I work on, but Euclid has been one of my favorites since I started my PhD. And now to actually be at the time where we're getting the first data and the first science on Euclid, it is incredible. It is amazing. This is so many people coming together in this effort. And this is how science works. Many people coming together with great ideas and just pushing us further and making this happen. It is very, very cool. Okay, I see some comments here. We need images of Tabby Star and Kepler. Yes, we do indeed. 66 minutes is a record for the CMB. That might be a new record, actually, yes. We have some clarification from Abyss about how the supernovas work here. How about the two stars, one being supernova. There's a comment here from Abyss if you want to read it. A few more comments very quickly. One from Lethargo. It may be too big of a question for now, but I'm wondering how you would characterize the distinctions, overlaps, and possible synergies between Euclid, Roman, and Rubin. So Nancy Grace Roman and Vera Rubin are future ground-based telescopes. That Rubin is a space-based telescope, right? Nancy Grace Roman is space-based, Rubin is ground-based. Those are all future telescopes that are planning to measure dark matter in different ways. Euclid, Roman, and Rubin are highly complementary. I'm not going to go into too much detail now because we are at the 1 hour mark, over 1 hour, but they're highly complementary. So Nancy Grace Roman is a NASA telescope. Rubin, I believe, is also NASA. But they're looking at dark matter. They're trying to find dark matter in different ways. So they're highly complementary. They're not competing against each other. And the places where they overlap, there is some overlap, and that is where we can kind of confirm that what they're doing is correct. Not going to go into too much detail now, but they're highly complementary, and there are regions of overlap that let you test what everyone is doing. Can Euclid lensing data be used to cancel lensing distortions out from the CMB? Probably not. I'm just answering questions quickly now. Probably not, because we're talking about vastly different scales. Euclid is looking at the lensing of individual galaxies, whereas when we look at the lensing in the CMB, we're looking at the lensing of the photons. So quite different scales, but the data will again be complementary. Because we can use the lensing of the cosmic microwave background radiation to measure how matter is behaving, you can do the same with all lensing to kind of create what is called the matter power spectrum, so how much matter we have on different scales. And there you would have CMB lensing data and Euclid data on the same figure. Have to answer this question by breath. Are there ongoing efforts to make an even sharper, more accurate image of the CMB? Yes. We are not done with CMB physics. Planck gave us that amazing map, but there is still the Atacama Cosmology Telescope ongoing, the South Pole Telescope ongoing. These are focusing more on polarization. Soon we're going to have Simon's Observatory, which is going to be a ground-based CMB mission that is aiming to stare very intently at the CMB in one patch of the sky. So it would not make a new full sky map, but it would give us a much more precise patch of the CMB map. And in the future, we're going to have CMB Stage 4, which is the next generation CMB mission. So there's a lot more to do with CMB stuff. That is a whole talk by itself, so that's not for now. Okay, almost an hour and 10 minutes. This has been super fun. And yeah, if you want one takeaway, is that Euclid is cool, and the images are cool, and the science that Euclid is doing is amazing. And I cannot wait until we get the cosmology results. It's going to be so much fun. Yeah, I love Euclid. It's such a cool telescope, such a cool thing that we've built and just threw out to space, and now it's giving us all these images. Very, very cool. I will never not be excited about new Euclid stuff. As soon as the press conference was announced, I went to my colleagues in the office who work on Euclid. I was like, "What's the gossip? Can I get the gossip?" I did not get much gossip, but a bit, and I was like, I can't wait for the press release. It's exciting. It's very, very exciting. So yeah, thank you everyone for being here. I'm going to change the video description to just be more clear that this is a Euclid talk, not cosmology news. This is first results of Euclid. As I said before, for anyone who missed it, the next few weeks, there won't be a cup of cosmology. I am traveling, then I'm having a party. So I think the next stream will be on the 23rd of June, probably. I might try to do one before then, maybe on the 9th, but it's highly unlikely because I literally get back from Cambridge that morning and I need to prepare for my other two conferences. So probably not a stream until end of June. So there's going to be a few weeks without streams, but there's plenty of old ones you can go and rewatch if you haven't done so. Again, if you haven't done so, like the video, subscribe, leave a comment, all of the usual YouTube things. It really, really does help. And for those of you on Instagram, there is now a Cup of Cosmology Instagram account where I am just posting announcements and advertising streams, and there's going to be some more stuff happening there soon. So feel free to follow that as well. Whew, okay, this has been super fun, everybody. Thank you for joining. Thank you for all the questions. Thank you for just letting me talk for an hour about cool space images. It's always fun. You're welcome to leave at any point, but I love that you stay here and listen to me just being overly excited about space images. It is very cool. Thank you everyone for being here. As I said, Cup of Cosmology will not be back for a few weeks, but I will be back at some point in June. And you're always welcome to reach out to me by email or by social media or whatever you want if you have more burning questions that can't wait. As you're all seeing, it takes me a while to get back to people if you email me, but I will eventually get back to you all. Real of Cosmology became real. yeah. Cosmic curiosities is also a thing that's on the horizon. Just keep that in mind. Okay, yeah, it is almost a month without Cup of Cosmology. I am aware, but there's plenty of old videos you can go watch, and maybe I do a bonus one, maybe from Cambridge, just like, hi, join me as I walk around Cambridge. We'll see. Okay, thank you everyone for joining. I hope to see you next time Cup of Cosmology is live, whenever that may be, and I hope in the meantime you'll stay safe and take care of each other.